I'm really concerned now whether it will get installed or not, because this is Eviews 8, quite an old version. There is not much difference between Eviews 8 and 10 or 11, which is running right now. I think 11 or 12 maybe, or even 13 for that matter. The core remains the same. Only some advanced options are added. That is the difference between open source software platforms and premium platforms, paid platforms. For everything add-on and other things, see, I'm going for accept. As you know, you should accept the terms and condition. It is choosing C drive. I'm letting it go. Generally, I choose D or E drive for these, but for this case, I'm letting it letting it get installed in C drive. Program files. Remember this path. It is asking for this again. Yeah. Let me write demo and see what happens. See, it allowed me. You write demo, it allowed me. See, many people were saying it is asking for serial number. I wrote the word demo, DEMO. I use the word option anyone who uses the computer. Press next. And now it is asking for what files to install. You let it install everything. But there is a trick here. Okay, let it install it in the path it wants to install. Yeah, this is very important. Here you should be careful, okay? There's a trick to fool you. It will ask you, would you like to block all users from receiving automatic product information update? If you allow update later on, it will again get blocked. So this is a trick they play. They are asking you, no, I would like Eview to check periodically, and yes, I would like to stop. Generally, we answer this kind of questions with a no, but you have to answer this question with a yes. So be careful with that. Okay, press yes. That is, I would like to stop Eviews from checking any updates. Press next. Let it do its business and let it install. It is getting installed. I just came home from university, so I had to get freshen up and get ready and set up. It is asking you the example file has been installed in there. You have to share shortcuts. Yes. Want to add shortcut? Yes. It has been done. Now you don't need to start Eviews. If it launches Eviews, you can close it down. This is the default Eviews folder. All right. Now we have a patch file. Okay, stored somewhere in your computer. So what I'll do is I'll right click on the patch file. You may not transfer it to the place where it is stored. You can directly try it here. Earlier it used to happen. You can press the option extract all. At the same place it will get extracted. Okay, it will get extracted at the same place. So now that this file is visible, it will only be visible if your antivirus is disabled. Otherwise it will get deleted automatically as a Trojan horse virus. The computer will call it a Trojan horse virus. It is not any kind of virus. Okay, this is their technique to prevent you from using cracks and pay thousands of rupees to them. That is why I prefer Gradle. Gradle are wonderful packages, wonderful tools, open source. Use it free without any stress. You get updates, everything, no worries. So then you double click on this patch. It will ask you for permission. Say yes. Once you do that, this kind of window, black, gray, embossed window will open. Just a moment. Yeah. All right. So just press the button patch. So it will say patch are done. Okay. So you press exit. Now you go to your start option, write Eviews, or on desktop you must be having the icon. Correct. I have the icon on desktop here. I am now opening it. Done. Voila, magic. Abracadabra. Done. Eviews is cracked. Open. You can now start using it. So I uninstalled from my computer and I showed you the installation again step by step. Most important part, disable the antivirus before starting on this. And you don't need to copy paste that patch file to your actual C drive Eviews where it is stored. You can just run it from anywhere. It will definitely handle it. I just did it in front of you. You just saw me doing that. All right, it is 6:30. Dr. Firdaus Malik, Dr. Ismail and others, let us start the session, please.
So yes, please, we should, move forward. So I will, make little introduction. On behalf of Jammu and Kashmir Economic Association, General Center for Global South, I welcome all participants for our third session. Today we are going to delve the third session. We are, going to learn today about classical econometric models. As you know, our, team resource person is Sam, Dr. Bhagirath, and we are having new moderator today, Owais Ismaeil, doctoral fellow from University of Delhi. So over to you, Owais.
Thank you, Dr. Firdaus. Am I audible to all?
Yes,
you are.
Yeah, thank you. All right. Hello, everyone. I'm Ismaeil, full-time doctoral fellow at Department of History, University of Delhi. I'm also serving as editorial head for Jindal Center for Global South, OP Jindal University. I would like to extend my heartfelt thanks to President JK Economic Association, Dr. Firdaus Malik, and also the Jindal Center for Global South, again for Dr. Bhagirath for giving me the opportunity to moderate today's session. We are pleased to welcome all the participants to the third session of this workshop. Today's session is titled as Developing the Classical Econometrics Model Using Eviews. We look forward to have an engaging and insightful discussion. Before we begin to today's session, I would like to introduce our esteemed and dynamic speaker, Dr. Bhagirath Baria, who has shown a great enthusiasm in organizing this workshop and leading our discussions. Well, he was introduced in the yesterday's session also, but we are aware that some participants may have missed it and joined us today. For the new participants, we are delighted to have Dr. Bhagirath with us again. And today he will guide us through sessions on developing the classical economics model using Eviews. A little introduction of the Dr. Baria is actually currently working as assistant professor in Department of Banking and Insurance, Faculty of Commerce, Maharaja Maharaja Sayajirao, University of Baroda. His research expertise spans various areas, including the applied macroeconomics, with special focus on macroeconomics of banking, international finance, and agriculture economics. Dr. Baria has a strong emphasis on applied econometric analysis, contributing significantly to these fields. He is the author of comprehensive book on economics published by the Routledge. Dr. Baria continues to engage in high-quality research, collaborating with both international and national institutions in field of economics, banking, and international finance. This was just a brief introduction of the Dr. Baria. I now kindly request all the participants to please reserve your questions for the end if you have any, as we will have a dedicated question and answer session at the end. Please maintain the discipline throughout all the sessions and write your questions in the chat box if you have. We will make every effort to address them all. I now request Dr. Baria to please take your session. Over to you now, sir.
Thank you so much, Mr. Owais. Very nice to again meet you. We met in the last workshop. We are meeting again, and it's a wonderful feeling. Participants, welcome. And yesterday we had a power pack session. Lot of engaging issues. Yesterday's session was actually a sign that we are having a very grounded approach on the topic, discussing those foundations, those philosophical issues about causality, discussing about correlation and how it differs from causality, how causality is manifested in social sciences, all those critical topics that we discussed, the important elements of an econometric model, the identification problem, how do you become a good modeler, a good empiricist, what kind of things you need to do. So those were the fundamental building blocks of becoming a good analyst. Analyst as in someone who can deal with data. And today we are actually going to get into the business of data, the actual hard work that we need to put in. And today's session, as I messaged you in the group, you keep having tea and coffee. You will require it. It will not be easy to simplify it. Econometrics is not easy. It is not a easy to learn science. You need to sit down, you need to work hard, you need to study. So start with your tea and coffee. I already had my coffee, you just saw me having it. So the same advice goes for you. I'll share my PowerPoint presentation screen. And the reason for having this PPT is to bring some ideas to the fore. And today's primary attention will be on developing these ideas. Unless we are clear on these things, it will not be possible to learn econometrics. What we are going to discuss yesterday, what we discussed was the building blocks of econometrics. Yesterday's session. Today, what we are going to discuss are the nerves and the veins of econometrics, the entire body of econometrics. These are the fundamental processes, ideas, concepts based on which entire science of econometrics is created. And with that idea, let me start my presentation, and I hope now the screen must be visible to all of you.
Yes,
Fine.
it's quite visible.
Yeah, thank you. So let us start with the business. Not going to be an easy session today. From point one, start having tea, coffee, whatever you want, whatever makes you feel fresh. Okay. Let's start with the business. And this is the session on developing the classical econometric model. Why we call it classical? Because it is the gold standard. It is the fundamental econometric model which should hold. Theoretically, it should always hold. In reality, it doesn't always hold. It is like the standard or the criteria that you have set for yourself to become financially free. That when I have this much of amount, X amount in my bank account, I will be financially free. That means I won't have to work. I won't have to pay any EMIs. I'll just move around my life, do whatever the hell I want to. Similarly, in life, you may be having certain criteria of what is success. That if I have achieved or purchased a house by this age, I'll be successful. Or if I have reached my career at this stage, by this age, I'll be successful. Those are criteria. Similarly, in econometrics, we have a set of criteria. These are the fundamental criteria. If these are followed, then the things that you are doing, the way you are handling your data will speak the truth. If these are not happening, you will have to go in deep, find out where is it missing, and then take the correct path that econometrics tells you. So consider econometrics as a textbook or a catalog or a menu. When you go to a restaurant to eat, in the restaurant you will have a menu that will show you the items, its composition, maybe its price, its category, what kind of food is it, and then you will choose out of it. Depending on how you feel on that day, you will decide what food to eat. Similarly, depending on whether these assumptions are being followed or not, you will decide which path to take to do your econometric work. So there are many paths, but they all origin from this classical econometric model. So we will look at these following important issues. The point one and point two will be discussed quite fairly quickly. And I have written the references also. I will share all these references with you. We will be sharing you with the Google Drive link for session-wise files, mostly after the workshop ends. So by then we will have time to collect everything from all the speakers, or I might prepare it in a day or two. You will definitely get it, but have a little bit of patience. We all are working full times. You are also working. We are also working. So by weekend, I'll be able to sit and plan out everything. So we'll start with a basic review of statistics, okay, which Dr. Parmit has already discussed, but I will just show you the topics that you should know about. It's fine if you are not completely clear about it. I will share the reading reference book also with you with that particular chapter, not the entire book, so you can read it peacefully and prepare yourselves. So this, whatever I share with you material, will give you a complete short course on econometrics. So after the workshop ends, start going through it. All right. Then we will look at the idea of experiments and causality in social sciences. This comes again and again because econometrics deals with non-experimental data, data which are not generated through randomized control trials, where you have a treatment and a control group and you have control over how and what kind of inputs or stimuli these two groups will be given. So you can clearly locate that because I did X, Y occurred. That clarity is never available in social sciences. Lot of X are working together on your Y variable. Lot of X are working together simultaneously on your Y variable. So what econometrics tries to do is it tries to take away those interfering influences of x2, x3, x4, so that the pure relation between x1 and y can be looked into. Okay, real world doesn't work like that, but scientific analysis needs that kind of knowledge. All right, for example, if my income, if you takes yesterday's example, if you increase the salaries of your employees in a company, their productivity has not improved. That doesn't mean that salary does not have an effect on productivity. That means you need to take into account other factors, control for them, take out their effect on productivity, and then see what happens with salary and productivity relationship. All right. So that is the idea. Then we will look into how regression analysis is framed in econometrics. What are the fundamental concepts and equations in econometrics? We will look into a two variable model. We will not get into multi-regression models. Multi-regression models are just extensions of two variable models. Some changes occur, but the fundamentals remain largely the same. Then we will look into the ultimate thing, the gold standard of econometrics, the OLS estimator, the ordinary least squares. It's not ordinary, it's extraordinary invention of the human mind. It is perhaps the most path-breaking invention in the history of quantitative sciences. And just because it is easy to estimate in packages does not mean it is easy to understand. Okay, there is good amount, very deep philosophy and very good grounding in the OLS estimator. What is this estimator? Why do we talk about it? We will see that. Finally, we will end with developing the classical linear regression model or the classical linear econometric model. All right. So let me start with the first session, the first topic, review of statistics. I'm not going to discuss all these things. Many of these topics have been discussed day before yesterday by Dr. Parmeet. You can always contact him more with this with these topics to discuss more about these topics. I will share Stock and Watson's book, wonderful book. I must be having it with me. Just a moment, I'll share it with you. Yeah, I have it. I have it in front of me. So I think there is a background issue, so it is not able to show it. No problem, I'll share the book with you. So in that book, chapter 3 gives you a complete review of statistics. What statistics should you know before you start your econometrics work? All right, all those things are very clearly given here. This is what you should know about. It's not very big. If you go sit down and read, maybe a week to grasp all these topics, not more than that. Assuming you're full-time, you're working full-time or a full-time research scholar. If you're a part-time research scholar or not working or working part-time, you should be able to handle it in 3-4 days. It's not very difficult. It's basic statistics, but these things are to be known because they are constantly used later on in econometric analysis. Where statistics ends, econometrics begins. That is how I like to put it. Second important idea is again about causality. In econometrics, we don't have the in social sciences, we don't have the luxury of conducting randomized control trials. So if you were to experiment on how increasing the salary affects productivity of employees, you would keep everything constant, just increase the salary and observe what happens to employee productivity. But that's not possible unless it's a very small scale. It is possible, but it is possible only on a very small scale. But if you are a corporate multinational firm having large number of branches and subsidiaries across the world, it's not possible to experiment like this. Because suppose if increasing the salary does not improve the productivity, are you going to again reduce the salaries of people? I mean, that's another problem. All right. So randomized control trials are not possible. If they were possible, you could see the effect of X1 on Y without worrying about how X2, X3, X4 are affecting your Y variable. All right, but that's not possible. So we try to do that using econometrics. The purest form of causation generally emerges from experimentation, but because we can't do that, we create econometric experiments. All right. So we create econometric experiments where we see the effect of x1 on y while controlling for x2, x3, x4, etc. And that's the scientific way of dealing with things. But it's not that easy. There is a lot of mechanics and lot of stuff going behind. Fine. Let me come to the key idea, regression analysis. We use the term regression quite often. Even most of the researchers who are dealing with empirical analysis tend to use this. So what do we mean when we say use the term regression? Namanda Gujarati being the foundational book, it defines regression analysis as the study of dependency, okay, dependency of one variable, that is the y variable or the dependent variable, on one or more other variables, the explanatory variables. What is the purpose behind regression? Very important. So it is so purely and clearly written with a view to estimating or predicting the population values. All right, very important, to estimate the population values. You want to know the truth. The truth is always in the population, not in the data set that you are having. It is just a sample which you have drawn or which came out from the larger population. Population, like Professor Shanmugan said, does not mean people. Population is any set of data in which you are interested, but you cannot access the information on that entire data set. So what you do, you take out a sample from it. Econometrics is concerned with the population, not with the sample. The sample is your compulsion. Your vision and aim is the population. So when you are estimating a regression equation, it is not that equation in which you are interested. It is you are interested in how well that estimated equation can represent the population you are interested in. Again, if you are having data on population, all these problems don't arise. Simply go for the estimation. Whatever comes is the final truth. That is not the case. You are generally dealing with samples. So whatever comes from sample needs to be used, so that you can know the truth about population much better. For example, salary, if it is increased by $1, improves employee productivity by, say, 5%. That is what your regression equation shows. Now, this is for your sample of 100 employees. You are having 10,000 employees in the firm or 1,000 employees in the firm. Can you use this estimate to represent it for all the 1,000 employees? Yes and no. Yes, if the tests that are to be conducted, which you will shortly know about, if they show the results are good, yes, you can do that. You can fairly confidently say that this is what would happen with all 1,000 employees, even though you have used data of only 100 employees. But if tests are not good, then either your sample is not good, maybe your sample was biased, it was not random. Essential, understand the heart of statistics, random sampling. You need to randomize as far as possible. If you are not able to randomize a sample, lot of biases will come in. It will be very difficult to adjust for those biases. Okay, so assuming that you have a random sample, if your sample is showing that salary is not having a impact on productivity, or it's having, let's say, 5% impact, is this true for all 1,000 employees? You had data only on 100 employees. Is this true for all 1,000 employees? Yes, if the tests are good. No, if the tests are not good. All right. So that's the idea. Econometrics is concerned with population, okay, not with sample. We deal with sample. We do tests on sample to be confident that this comes from the correct population. If those test results are good, we are fairly confident, yeah, this represents my population well. If the tests are not good, you are not confident that this represents your population of interest. Now, what are the key concepts to be taken away from this? The first concept is dependency. Okay, regression deals with dependency. How one variable y is dependent on x. I'm not taking into account multiple regression model. I'm assuming there is only one y and one x. All right, for now, to keep the matter simple. You can always read and extend this to a multi-regression framework. The fundamentals will largely remain the same. 95% will remain the same. So how is y dependent on x? That's the question. Dependency. This comes from theory. It can't come from econometrics. Okay, regression does not imply causation. We will see that. Okay. A dependent relationship. What is the dependency? What is the form of that dependency? You know, what kind of equation are you talking about? Is y a function of x where x is in log form, linear form, in log linear form? What kind of, or a quadratic form? So y is a function of x and x square, or y is a function of x and x cube, or y is a function of x, x square, x cube. I mean, what's that exact form? Mathematics will guide you in this. Maths will guide you here. Now, again, next question. What x variables to use? What y variable to use? Theory. Okay, there also you need theory. You can't use knowledge of statistics and econometrics in that. If you are using that, you are doing wrong. Okay, you are doing wrong. Then, very important, okay, the population value. Based on your sample data, sample regression, what is the expected value of that sample regression? Is it equal to or near or within a range of population value? How would you answer this question? Statistics. Okay. And now if you combine all these things, that is, if you ask a question, what will be the effect on sales of my firm, of my company, if my firm increases the price by 10%? Okay, if my firm increases the price by 10%, what will be the impact on the sales? This is not a demand function. Okay, it's a sales function. So if you increase prices by 10%, how much are my sales changing? Are they increasing, decreasing? If increasing by how much, if decreasing by how much, is there any impact? To answer this question, you need to combine your subject knowledge, your theory, statistics, mathematics together. Then you can have econometrics. All right. So that is what regression does. Regression is concerned with the population values, not with the sample. The data that you are having is but only a reflection of the larger population, which is hidden from you. And you need to use this sample information to extract that truth about the population that you are interested in. Fine. Some core fundamental concepts, or there are two kinds of relationships that we look into, statistical relationships or deterministic relationships. Deterministic are quite clear. Y is a function of x. Enough, done. You know, in pure science and science, in physics, we have many equations like E is equal to mc square. It is with 100% accuracy that you can claim that E is equal to mc square. And if there are errors, they are so minute that you can almost neglect them. Okay, that is a deterministic relationship. Y is a function of x. You are not introducing the error component, the disturbance, the error component in this. But if you introduce the error component, you have a statistical relationship. Okay, because now you will have to handle not only with x, but also with that E, error component in your equation. That will also start behaving and doing stuff, and your Y will also get changed because of that. So you have to deal now with two things, not just x. Earlier you had to deal only with x if it was a deterministic relationship. Now you have to deal with x as well as that error if you are estimating a statistical model. All right, very important to understand this idea. How are regression and correlation different? Well, while we all discuss about this and know, very important is that correlations are measures of strength of linear association, strength and degree. Okay, how strongly and in what direction are two variables linearly interrelated or associated, I would say. All right, so there is good amount of symmetry. Both are random. X and Y both are assumed to be random. They can be random in correlation analysis. That's not the case in regression. There is no symmetry in regression. There is asymmetry. Okay, there is asymmetry. Why? Because in regression we assume that while Y is a random or stochastic variable, X may not be or should not be. Even if it is, it has to follow some properties which will make its randomness fizzle out, cancel out. So that's the fundamental intuition you should have why correlation and regression are different. Regression is asymmetric. It treats Y as a random variable, but not X. Okay, even if X is, which is quite natural, expects certain kind of behavior from X, so that randomness in X can be controlled and managed. Okay, it can be manageable. You can't remove it, but you can manage it. Of course, regression, if it is good, does not mean there is causation. If you regress Y and X, that is, you regress Y on X, and your relationship comes out to be very good, does not mean that X is causing Y. Theory will tell you, your theory, your subject knowledge, the reality, what is going on in the real world, that will tell you whether this makes sense, like Bhagirath's sleeping hours and the Indian stock market. Okay, you can take any two data sets and run regressions on them, and you might find something useful. That doesn't mean it is useful. Okay, very important to understand this. A very important point on this slide to be remembered or absorbed, and if you're making notes, you can note down this critical point. Independent variables are assumed to be fixed in repeated sampling. Now, what is this idea of repeated sampling? See, you have a population, but you don't have data on entire population. So you will have a sample. Let's assume theoretically that you could keep collecting samples from that population. So what's the population? Let's say all the people in your country, or all the firms, companies in your country. You are interested in them. What are you interested in? How will increase in tax affect corporate performance? Very practical question. How will increase in corporate tax affect corporate performance? Very, very natural and practical question that we can think of. Now, in this, the Y variable is corporate performance. That is what you are interested in. It is assumed to be random. Okay, it is assumed to be random. But X variable is not assumed to be random. What does this mean? Suppose from that, let's say in your country there are 1,000, or let's say 1 million firms. There were 1 million firms in your country, and I take a sample size of 1,000 firms from 1 million firms in your country. I close my eyes and randomly start drawing 1,000 firms. The first time I draw 1,000 firms, I will have data on Y and X, corporate performance, corporate income tax. Second time I do it, again I will have data on Y and X for each firm. Okay. Third time I take out sample of 1,000 firms, I will have another data set. What we are assuming is, in this process, your independent variables will remain the same. So every time you draw data on Y and X on a new sample from that population, your X should remain consistently fixed. In other words, you should be able to get the same X multiple times if you are running this kind of experiment. That is, you are drawing samples of the same size from a given population. That's the idea. All right. It's fine if you don't completely understand the idea, but some intuition has come to you. Once you read, you will be able to understand the foundations of this. Why is this done? This is done to ensure that already for Y we are having an E component, error component. Now, if X also has an error component, now you have two error components. So you will have to handle those two error components and try to manage the things. It will complicate the matter a lot. Okay, so that is how econometrics has been developed. It can handle these problems well. Okay, later on we can relax these assumptions and it can handle it fairly well. Fine. So these are the fundamental things you should know. Let us look at the two variable regression model. How would it look from an econometric point of view? Two fundamental concepts that I would like to touch: the population and sample. When you are estimating a regression equation, you know by now what is a regression equation. Y is a function of X. Okay, it can be X1, X2, X3. We are assuming Y and X, one Y and one X, as simple as that. So Y is a function of X is your regression equation. Let's say Y is equal to beta 0, which is your constant or intercept term, plus beta 1 into X, plus your disturbance term. Now, this equation is actually the population regression equation. It's the population equation. That is, you are interested in all the 1 million firms in your country. You want to see how corporate income tax will affect their performance. So your actual equation is about the entire population. Try to grasp this idea. When you're creating an equation, any kind of equation, whatever Y or X variable you are analyzing in sociology, in political science, in HR management, in marketing management, whatever it is, that equation is reflecting the population you are interested in, not the sample data that you will have. This is the idea. So there are two kinds of regression equations: the population regression equation, but you can't see that, you can't know the numbers from population regression equation because you don't have data on population. If you had data on population, wonderful for you, no need to do all these things, simply estimated, whatever comes out is the final truth. That's the reality, no need to go further. But in reality, what happens? We have sample data. So while we are estimating the population regression line or population regression equation, that is what we are interested in. We have data on sample, so we estimate a sample regression equation. All right, very important. You will understand it very soon. I'll again show you on slides along with diagrams. All right, so this is the idea, expectations. Okay, the expected value of y given x is a function of x. What does it mean? It means on an average, if you keep taking out samples of that 1000 firms from those 1 million firms, if you keep taking out samples of 1000 firms, okay, for each level of x, okay, for each level of x, that is for each level of corporate income tax, you will have firms which have different profits. Very, very easy to understand for you. See, in your country itself, government may be charging different corporate tax for different sizes of firms, for small, for medium, for large, even within them based on industry, products that they are making, whether they are, what kind of service they are selling. So for each income tax, for corporate income tax rate, let's say 10% corporate tax rate, there will be lot of profits, lot of y variables. Similarly, for 15% corporate income tax, there will be companies in your sample, that 1000 sample, which will have many different profit levels. Some will have low profit, some will have medium profit, some will have high profit. Similarly, at very high corporate income tax rate of 50%, again, you will have firms which have different profit levels. What this equation says is that if you keep your x constant, that is for profit of 10%, if you keep taking out 1000 firms from the sample which are having tax rate of 10%, you will have a whole range of profit levels, y levels. The average of that, okay, which is its expected value, is a function of that x. As simple as that. In other words, y is a function of x. But this time we are looking at y, lot of y's for one single value of x. And this should be true for at each value of x. So for each value of corporate tax rate, 5%, 10%, 15%, 20%, 25%, the whole range of profits of the firms at each level, okay, at each level is a function of that x itself, at each level of x. That's the idea we are trying to bring out. In other words, on an average, your regression equation, okay, whatever regression equation you are estimating, you are interested in y variable, that y variable, okay, that y variable should at every level of x, okay, at every level of its own y, should be a function of the x variable at that level. Till now we were thinking of y and x, but you have 1000 firms, so you have 1000 y. Fair enough, you have 1000 y's. Each of the y is a function of the x at that level. So for a firm of, let's say, a profit of 5 million US dollars, it is a function of x, which is, let's say, 20% at that. So this should be true not only for entire y and x, all y and all x, it should also be true at each y and x pair. At each pair, this dependency, y is a function of x, should also be there, and it is there. Okay, because at each level of x, y is dependent on x. That is why we say y is a function of x. Okay, so that is the idea we are trying to throw. It's fine if you are not able to completely grasp. Read it. I will give you a lot of reading stuff. This is not very critical, but you should have a fair idea about it. So this is x, but we want to understand it in form of equation, which we can practically use. So equation is given in the second equation. Expected value of y given x is a function of beta 1, which is a constant term, okay, plus beta 2 into xi, okay, x. So in our case, what is y? It is the profit of the firm. And what is x? The corporate tax rate. So expected value of profit given corporate tax rate of say 10% is equal to beta 1 plus beta 2 into 10%. Okay, because corporate tax at that point is 10%. So what is true for all y and x should also be true at each observation, for each level of observation. Okay, this is a very fundamental idea behind regression. Okay, so this is the population regression idea. What are the key concepts? Firstly, regression coefficients, beta 1 and beta 2. Beta 1 is the constant term. Even if you remove x from the equation, make it 0. So beta 2 into x, which is 0, will be 0. Beta 1 will still be there. That's your minimum value. Like I gave you example yesterday. If I stop consuming, if I stop earning income, doesn't mean my food consumption will become 0. Food consumption is a function of income. But even if income is 0, food consumption will go on. That's beta 1 value, minimum value. So those are regression coefficients, beta 1 and beta 2. They show the impact of x variable on y. Beta 1 is the constant term. It shows the minimum value or the constant value of y when all x variables are absent. Fine. We have used the term conditional distribution. You can see E into bracket y given xi, very important. We are not only interested in y, expected value of y. Expected value of y is just the mean value of y. You must be having data on your y, profits of 1000 firms. Take an average, that is the expected value of y. Expected matlab, that means the average value here. We are not interested in the average value of y. We are interested in the average value of y given x. So we want to take into account the effect of x on y. Okay, that is what we are interested in. That is known as conditional distribution of y. Linearity, we will discuss. Okay, we will discuss about linearity, what it means. Let's go on the next one. So this is how a population regression function would diagrammatically look like. Okay, it's an estimated regression equation. The idea that I was trying to throw at you, weekly income and weekly expenditure. Okay, for weekly income of $80, okay, you can see the lowest one, 80. For weekly income of 80, your consumption expenditure is not fixed. There are so many different kinds of consumption expenditure. There can be 60 rupees, $60 consumption expenditure, 70, 80, 90, 100, you know, lot of different kind of consumption expenditures are possible for somebody who has income of $80. So if you have data on houses, thousands of houses, the houses which are having income of $80 per week will not have the same consumption, will not have the same expenses. Even for houses with $80 income, there will be a lot of different kinds of expenditures. Okay, that idea is shown here with those points. Those small points are those different consumption levels of the same house. What does it mean? Even if somebody is earning only $80 per week, they might choose to spend a lot on food, on going out. They might not be interested in saving. So their expenditure will be on the higher side. Those who are earning $80 might be quite smart. They might spend less, save more, and invest that in mutual funds or stocks. So their weekly consumption will be on the lower side. Okay. So at each level of X, 80, 100, 120, 140, you can see there are a lot of dots. There are different kind of expenses. Similarly, look from our example. For each level of corporate income tax, $80, $100, $120 corporate income tax, you take any one corporate income tax level, let's say $100 per week, just an example, okay, dummy example, $100 per week. There will be firms which have different profit levels. Okay, there will be firms which have different profit levels. So what is the expected value of y given x? The expected value of y, okay, given x is 80, is given by this big black dot, which is connected to a line. Similarly, the expected value of y, that is, let's say the profit of the firms, given corporate income tax of 100 is given here in the middle. Okay, a big dot. Okay. Similarly, at 120, we have another big dot, which is almost at the central, which is at the middle of the data set. It is a central location. Dr. Parmit must have talked with you. So central tendency is very important. You take central tendencies at each level of X, connect them, and you have a big black line that you can see here, bold line. That is your population regression function. Okay, this is what you are interested in. All right, this is what you are interested in. Now look at this. The same idea expressed in a different way. Okay, the same idea expressed in a different way. Let me switch off my WhatsApp because it is disturbing me. Now it won't disturb. So the same idea. All right, the same idea is given here. At level of 80, okay, weekly income, there may be thousands of houses in your sample which have a weekly income of 80 US dollar. They will have very different consumption pattern, expenses, food expense, etc. So if you look at the distribution of food expenses for the houses having a weekly income of 80, you will have a distribution there. Okay, you can see a bell-shaped distribution, a normal distribution here. So in our corporate tax and profit example, for a given corporate tax level, let's say 10%, you have 1,000 firms you will have many firms which have different levels of profit. The expected value of that distribution is at the middle point, which is given here. That double dot is there, one dot is there and circle is drawn around it. So you keep on hitting on that expected value, which is the average value of that distribution of Y for a given X, and you keep connecting them, you get a population regression line. That is what regression does. It tries its best to pass the line through the average of the distribution of Y for each level of X. Okay, very important idea. For each level of X, population regression function tries to pass a line, okay, connect the points at the central tendency, at the expected value. Expected means the average value. Which average value? Conditional average, dependent on the value of X, not the simple average of Y, on the conditional average of Y. Average of Y given the value of X. Here the given value is 80, then the given value is 140, then it is 220. Connecting all of them gives you the population regression function. Okay, what is linearity? We'll talk about this. In econometrics, linearity is assumed. There are two kinds of linearity. You can have a linear in parameter model, a linear in variable. What are parameter? In the population regression equation, the actual equation which you are interested in, which are trying to estimate, understand, you have regression coefficients, beta 1, beta 2, etc. Those are parameters. If you are talking about population, okay. Otherwise they become regression coefficients or estimated coefficients if you are talking about the sample. Those parameters, okay, if they are linear, that is, you don't have square and quadratic terms, okay, then you are dealing with linear econometrics. This is different than what we study. Let's say Y is a function of x1 and x1 square. Or let's just talk about Y and X. Y is a function of X and X square. In econometrics, this is linear model. So in statistics, it may not be called linear. Why? Because you have X square also. But the effect of X square, okay, on Y is linear. That is the parameter, the coefficient is not in square. But suppose if I create an equation, Y is equal to beta 0 plus beta 1 into X plus beta 2 square, beta 2 raised to 2 into X square. Now this is not a linear econometric model. Now it has become non-linear econometric model. So we talk about linear in parameter and linear in variable. In econometrics, we are interested in linear in parameter models. So you can have X square, X cube, Y square, Y cube, X into Y, no problem. You can create any combination of X, X1 into X2, X1 square, X2 square, X3 square, X4 square into X. You can do whatever the hell you want to do, but the associated coefficients, parameters, those betas, they should not be squared. They should not be cubed. Okay, they should be linear. Okay, that's the idea when we talk about linear econometrics. Very important to understand this. So till now we did see, in this case we did not allow for any error term. If you see the equation here, there is no E or U disturbance, but now we need to allow it because errors can occur even in the population. All right, errors can occur in the population. So why? Because see, if you have an equation that expected value of y given x is equal to beta 1 plus beta 2x, does that mean that your x will explain everything about y? Of course not. There will be a lot of other stuff going on which you don't know about. Even in your population, you don't know about what is. So for example, corporate tax will have an effect on corporate profit, but a lot of other stuff can have effect on corporate profit. So we introduce the disturbance term, the U term. Okay, that is why we introduce the U term. Yeah, the Dr. S. Raja has asked, the idea is applicable for both the population regression and the sample regression function, 100%. We will discuss about sample regression also. And yeah, it was a normal distribution curve, Miss Arshia. It was a normal distribution curve. That is correct. Sometimes it may not be normal, then you have to do other kind of things. The role of constant, I will let you know later. Okay, we will discuss that. So now what happens? Now in your population regression function, y is made up of two things. It is made up of a deterministic component given here in the next equation. Y is equal to expected value of y given xi plus ui. So what is this y? Actual y that you can observe. That is equal to what? It is equal to the estimated y plus a disturbance. Why we have an estimated y? Because we are running regression. When you run regression, you already have, see, very important, you have data on y, you know x, you want to see their relationship, and when you do that, you create an equation, and when you create an equation, you start predicting or forecasting values of y. But you already have y, you have data on y, actual y seen in the real world, but your model is also predicting y. So the actual y is contains the actual y is the y that you have seen, observed. Your estimated y, where does it come from? From the regression plus an error, because your regression will not be perfect. It will always miss. Okay, it will always miss the actual y. Okay, you can't have a 100% perfect regression equation. It is impossible. At least in social sciences, you won't have 100% perfect regression equation. So what is actual y that you are observing is equal to two components, the y that you have estimated using regression, and then the error term or the disturbance term. For population regression equation or function or equation, whatever you want to call it, we call it disturbance. In sample, we call it residual or error. This is the language. So what is your error? Ui shown here, disturbance, is equal to actual y minus expected value of y given xi, which is your regression equation forecast. Using regression, you have estimated the value of y. Now, if you take actual y, subtract from that actual y the estimated y, whatever number is left plus or minus is your disturbance, your error, your lack of knowledge. It is your lack of knowledge. And this is what econometrics deals with. It tries to bring this disturbance in a randomized fashion. It tries to make it random. So once it is random, there is nothing systematic. So really you can't do about it. It won't have any significant impact on your analysis, on your y. But if it is not random, then it can create problem for you. So econometrics and econometricians spend a lot of time to make this random. Okay, and they do a lot of stuff to make it random. Why they do that? It will be clear to you. Okay, in this session and as well as in other sessions that go on after this. So the stochastic term is the foundation of econometrics. The entire science of econometrics is built on this disturbance term, error term, or stochastic disturbance term, or stochastic term. It is in the population. See, we are always interested in the population side, not in sample. Sample is something you have to deal with because you don't know the population. All right, but econometrics is concerned with the population. So why do we have a stochastic term or a disturbance term or a error term in our population regression function or even in sample regression function? We have it everywhere. Why? Because there are several factors which are chance elements, random in nature. COVID-19, when it occurred in India, lockdown occurred. We did not know about it. Nobody predicted it. Okay, nobody expected that. Lockdown occurred and changes occurred. So there are changes which are not in your control. So you can never forecast its effect on your Y. For example, corporate tax rate will have an effect on corporate profit. But suppose recession starts in the country. So corporate profit, even if tax rate is being reduced, still corporate profit will keep on falling because the recession is started. So I mean, there are elements that you don't know about or you can't control. So you have to allow that. You have to be humble enough to accept that you don't know everything. You have to be humble enough. The second thing that comes is measurement error. There are times when you don't measure your x variables correctly. So at that time also, that measurement error will enter into that disturbance term quietly. Okay, that measurement error will enter the disturbance term quietly. Rupanshi, I will answer your question soon at the Q&A round. You do ask me about it. So measurement errors can occur because we are talking about large scale variables which affect the whole country or a city or a community. Errors will be there. Okay, you won't be able to perfectly collect data. So all those errors that you are committing, the more error you commit, the larger your disturbance term will become, the smaller your regression equation will become. Okay, so you have to be very careful about quality of data, what kind of data you're selecting, whether it is well defined, whether it was collected randomly or not. And then lastly, you have human indeterminacy. Matlab, there are some things you don't know about. I mean, where is God, for example, if I ask you that question? I mean, I don't know. It is a belief. It's my strong belief that that entity is there. But I mean, I can't prove it to you. You know, many of us experience it. Many of us in our lives at our bad times, perhaps, we have prayed and the prayer has been listened. And we felt that, but we can't explain it to somebody. We can't go and measure it and make it convert it into a number. Or if you meet somebody, you feel very happy meeting them. You are meeting them for the first time, but you are feeling very happy. For example, you must be feeling very happy meeting me in online mode, isn't it? I hope so. But we have never met earlier, but somehow it is good. Next time when we meet, you might be very angry on me, or you might not even like to look at me. I mean, human nature is quite random. What will you do after 10 minutes? Even you don't know. I mean, what will you be doing? So there is a lot of randomness in the real world. So that disturbance term will capture all those randomness, errors, your lack of knowledge. So what econometrics does, it tries to keep it random and manageable. It tries to keep it manageable. Okay. This is a sample regression function, same population regression function, but because we don't have data on entire population, we have only a sample data. So we use a sample regression function. This is the regression equation that you are going to estimate. Which one? The last one shown on the slide, the lower one. Yi, that is your actual y, is function of estimated beta 1 plus estimated beta into xi, which is your x variable, plus your estimated disturbance, which is the residual. So when you use the term residual, it is in the sample regression function, actual equation that you will estimate. What are you trying to understand? The equation written above it, the population regression function. So I am estimating the effect of corporate tax rate on corporate profit for 1000 firms because I have data on 1000 firms. But what am I actually interested in? I am actually interested in, my actual problem is, how will corporate tax affect corporate profit for all the 1 million firms in my country? All right. So by using that sample equation, estimated equation, and its various estimated values, you want to talk or speak or know something about the larger population. That is what econometrics deals with. Okay. It teaches you, gives you tools where your sample regression function, which the actual regression equation you will estimate with your data, will be as close as possible to the population regression function. So if I have data on 1000 firms, and I find that corporate income tax has no effect on profit, then that doesn't mean, it may mean, it may not mean that all 1 million firms are also not getting affected by corporate tax rate. It depends. Okay, you need to do tests, you need to do good econometrics. There are methods that you will learn about, based on which you will be able to see whether your sample regression function is able to represent the population regression function or not. Okay, that's the fundamental idea behind doing econometrics. You deal with the last equation, the lower one, but you are trying to know about the upper one. Okay, that is the idea behind econometric work. This is a very good idea of keeping PRF, population regression, and sample regression function together. If you see this diagram, weekly income is given on X, consumption on Y. For one given value of X, okay, here at Xi, the expected value of y given xi, that is your true value, okay, expected value of y given xi, population regression function value, actual true value is given here. Expected value of x given y given xi. But you don't know about this. You don't have access to population data. If you had access, why do you want to do all this? Why do you want to talk about sample and hypothesis testing? Just go for your population data, run a regression, whatever comes is the final truth. Debate is settled. But that's not the case. What you actually get through your regression equation, you will get a estimated y cap shown here. Okay, y cap shown here. This is what you will get from your actual sample regression estimated equation that you will work on. But you will also have data on actual y, the top one. Okay, in this case, we are assuming actual y is more than the population value. Okay, it can be other way around also. So nothing to worry about. So what is happening here? The actual y that you are observing is given here, yi on the top. The estimated y based on your regression equation that you are run in the software, okay, that equation is giving you an estimated value of y cap. The difference between the topmost y and your estimated y is your residual. See, u cap, residual. But the difference between actual y and your population value of y, expected value of y given xi is u without a cap, which is your disturbance term from the population regression function. Okay, from where? From the population regression function here, this u. Okay, you can see this u term here. Okay, you can see this u term here. This u term is given here. The difference between the population value of y, actual y in the see, actual y, this, what is this y value that you are having? Actual y. It is an observation, one sample that you have drawn from the population. Then you are running a regression using it with x, and then you are having an estimated value which is y cap. But still you don't know the true value. What is the true value of population? Let's say the true profit. Okay, the true profit at income tax of 10%, which is your x here, xi. Let's say income tax of 10%. What is the true level of profit at that level? True average profit for all the firms put together. That average, you know, that distribution, bell-shaped distribution, the central point of that. You don't know that. Okay, you don't know that. That is what this y given xi shows. But what you know the actual y that you have taken as a sample from that population, and you have another y which is your estimated y, regression y cap. The difference between actual y and regression y is your u cap or your residual term. So you use this is the idea behind sample regression function and population regression function. The question comes now is, how do I make my sample regression function, that line, that there is a smooth line which is the PRF, and then there is a line with breaks, that is the SRF. What do I do to make my SRF come as close as possible to my PRF? In other words, how should I use my sample data, actual sample data on y and x? How should I use it so that when I estimate my regression, what do we mean by estimating regression? Estimating those coefficients, beta 0, beta 1, beta 2, etc. How do I estimate those betas? Because y and x are already given to you. So what you are doing new is betas, those coefficient, constant term, then beta 1, beta 2, however many x you have. How do I estimate those betas so that my sample regression function can come as close as possible to the population regression function? Okay, there are a lot of answers for that. Okay, we will look into that answer. The most fundamental answer is the ordinary least square estimator. So you estimate your beta cap. See this equation, the new equation here. Yi is beta cap 1 plus beta cap 2 into xi plus u cap I. So you estimate your beta 1 cap and beta 2 cap using OLS under certain assumption, and in that case, it will be closest to your population regression function. So you can be very sure that if your corporate tax has a positive negative impact, okay, so increasing corporate tax reduces profit for your 1000 firms. If it follows certain assumptions known as the classical linear regression model assumptions, then under those assumptions, ordinary least square is the best estimator to calculate beta 1 and beta 2s. If you do that, you will have the best possible result. No other estimator can beat it. If those assumptions are not followed, then try to bring those assumptions back, make the corrections or adjustments, Still, if it is not happening, then you go for other kind of estimators like instrumental variable estimator, or you can go for we have this stepwise regression estimators. Lot of other things are two-stage least square estimators are there, partial least square estimators are there, but you use them only when OLS is violated and you have a strong reason, just justification. We will see what is that. Okay, so this is the sample regression function. This is how it would look. This is the equation you will estimate with your sample data. Okay, this is the regression equation that you will estimate. A very important line is written in statement is written in yellow colored. In other words, how should the sample regression function be constructed or created? That equation given on this slide. How should that equation be created so that beta 1 and beta 2 are as close as possible to their population values, which are the parameters. Okay, where are those parameters? Those parameters are here. You can see on the screen. This beta 1 cap, we want to estimate it in a manner that it is as close as possible to beta 1, which is the population value, population constant term. Similarly, this beta cap given here, or beta 2 cap, okay, which is the estimated effect of corporate income tax on corporate profit. Okay, it should be as close as possible to the real world or real thing. What is that real thing? For all 1 million firms put together, but you are having data of only 1000 firms. So you have estimated your beta effect of income, corporate tax on corporate profit using those 1000 firms. But if you, what should you do so that this number that comes out, this estimate, is as close as possible to the population value for all the 1 million firms put together? Because you have data on 1000 firms, but you want to make a policy for all the firms. Government is not going to change income tax or corporate tax just for 1000 firms. It will be changing it for everybody across the board. Okay, so that's the question here. So how do you do that? How do you use sample regression function, and particularly beta 1 beta coefficients, okay, those regression coefficients in the sample regression function? How do you estimate them so that they are as close as possible to the population regression function? So that is the idea behind using econometrics and doing all the things that you do in econometrics. Okay, by now you understood a very fundamental idea that the main problem in econometrics is to estimate the PRF, population regression equation or function, based on the SRF. In other words, how to estimate the regression coefficients. See, y is given, x is given. You don't need to estimate them. You already have sample data on y and x. So in your regression equation, what is new that you have to work out, find out? Your beta coefficients, your constant term and your slope coefficients. Beta 0, beta 1, beta 2, howsoever many x are there. That is what you are interested in. So in other words, how do you estimate those regression coefficients, betas, so that they are as close as possible to the population parameters, population betas? So there are sample betas or sample coefficients, there are population coefficients, which are parameters. You want to take your sample coefficient as close as possible to the population parameters. How do you do that? Two major methods are well-known methods are available: ordinary least squares and maximum likelihood estimators. Fundamentally, it is the ordinary least square which is used. MLE is also used only when there are some limitations or violations in the OLS. So try to understand, OLS is the gold standard. Making some change, one small change in OLS, you have a new method, so-called new econometric method. It's not a new method, it's a new estimator actually. Okay, and then you make another change here, you have new econometric estimator, or what we popularly call new econometric method or technique. Those are not techniques actually, they are techniques about estimators, those coefficients. How do you estimate them? Equation remains the same. The population regression function, sample regression function remain the same. Your y remains the same, x are also the same. How do you combine them to create those coefficients, betas, so that they are as close as possible to the population value? That's the main concern of econometrics. Two answers generally, minimum two answers are given, even others are there: OLS and MLE. OLS is the most solid one because it has been proved to be consistently outperforming others. And even when there are violations, still in many cases, OLS remains the best one. When you will understand with as the sessions go by, you will definitely understand. All right. Yeah, somebody is asking for previous slide. What is the difference between observed value and true value? True value is the population value, which is what you are interested in. You don't know that. Okay. So what is the effect of corporate tax on corporate profit for all 1 million firms? That's the true value. What are you interested? What can you see when you collect data? You can see the actual values of corporate tax rates and corporate profits. Okay. And then you estimate using a regression equation. That estimated coefficient is your observed value. But you are interested in the true value. The population regression function shows the true value. Sample regression function shows the observed value. All right. So why is there two equation? Because there is population regression function, which is what we are interested in, but we can't estimate it. We have sample data, so we estimate sample regression function. But whenever you are dealing with sample regression function, the actual equation we are doing it, we need to think and see, ensure that it is as close as possible to population regression function. Okay, we'll get into that shortly. Okay, some three important concepts: parameters, those are the regression coefficients in the population regression function, your regression equation for the population for all 1 million firms put together. Estimators, those beta coefficients are estimators. Why they are estimators? Because they combine sample data on X and Y, and then they create an effect of X on Y. So they are estimators. What are they estimating? They are estimating the effect of X on Y. Say X1 on Y1, so beta 1, X2 on Y2, beta 2. So beta 1 and beta 2 are what? They are estimators. When you actually run regression, you will have one value that is known as estimate. So econometrics is not concerned with estimates or parameters. It is primarily concerned with estimators. You make your estimators solid, nice, scientifically good, so that whenever you use that formula or recipe, the final product will always be good and it will always be as close as possible to the actual thing that you wanted. For example, if you know how to cook a certain dish, you know the recipe very well, freshly baked bread at home, for example, if you want to make that freshly baked bread, okay, at your home, if you know the recipe outright, you are an expert on that recipe, a master chef, you know every single ratio and proportion by heart, and your hands are trained so well, you cannot commit any mistake. Every time you work on that recipe, the bread will be wonderful, it will be the best possible bread, and it will be as close as possible to the kind of bread that you want your customers or your family members to eat. Okay, so what your family members want to eat? Parameters. Okay, how would you create it? Estimator, the recipe. What are you actually making? The actual bread that comes out of your oven, which is the estimate. Econometrics says, let's make the estimators nice, compact, scientifically strong, so that we don't need to worry about either the parameters or the estimates. They will always be close to each other. That's the logic. Okay, that's the logic behind econometrics. So for example, we can create thousands of formulas. You can take data on Y and X and create hundreds of different formulas, and then every time you can create a new estimate. For example, I can say that the effect of corporate tax on corporate profit is 10%. How did you get it? It's here in my brain. I have an estimator. I cannot convert it into a equation, but it is there in my brain. That's the answer. So I can create some formula also for you, which is correct as per my need. So there can be thousands of formulas, okay? But what we want is a formula or an estimator which is good, which is scientifically correct. So if you are baking a bread, you want to bake the bread by using the principles of baking. You don't want to overheat, you don't want to put too much of yeast in it, you don't want to disturb the scientific nature of that particular recipe. So OLS turns out to be the best estimator in this case. Okay, OLS turns out to be the best estimator. What are the parameters for corporate tax and performance? See, the effect of corporate tax on performance is a parameter. If you're talking about all 1 million firms, the population. But if you're talking about only 1,000 firms, sample data, then the effect of corporate tax on profit is regression coefficient or sample coefficient. Okay, very important. Parameter is a relationship. It's an estimator. So parameter is an estimator. Okay. Parameter is not an estimator. Sorry. Let me correct myself. Parameter is the actual truth, the actual effect of X on Y in the population. But how do you calculate that? What's the formula, recipe to calculate it? It's the estimate. How do you do that? Using sample data. So what will you get? you will get estimates. Now, what you want to do, you want to take this third one, estimates, as close as possible to the parameters. Okay, you want to take this third one, estimates, as close as possible to the parameters. What is your bridge between the estimate and the parameter? You rightly understood, the estimator, the formulas, the recipes. Okay, the recipes. Fine. We'll go ahead next. Some things are there which are too detailed. You need not worry about them right now, but I will share the PPT, you study it. This is the idea, definition of an estimator. An estimator is simply an algebraic function. Okay, estimator is simply an algebraic function. It's a function of sample data. Okay, estimator, it's a function of sample data. So when you calculate beta 0 constant term or beta 1, beta 2, you're using sample data, actual data that you collected as sample on y and x. But once you use that formula and you put the data in it, plug the data on y and x, you get some numbers. They are known as estimates. Okay. Now, how do we know which is a good estimator and which is not? In econometrics, we use repeated sampling method. So we do a thought experiment, or we can run Monte Carlo simulations also in computers. We create a population, dummy population, or the actual population we are interested in. We look at it, look at its mean value or standard deviation. What should be there? We may not know the numbers, but we try to understand the distribution. What is distribution of a variable? Its mean, its standard deviation, two major moments of a distribution. So you take those two moments of distribution of a population and create a population and start drawing out sample from that 1 million firms. Start drawing out 1,000 firms randomly, constantly. Keep drawing them out, keep drawing them out. What will happen? Every time you have a sample, you can estimate the beta 0, beta 1, and beta 2, you know, for each sample of 1,000. So there's, let's say you have 10 samples. So you will have 10 different estimates of beta 0, beta 1, beta 2, beta 3, however many x are there. Assume there is only one x. So beta 0 and beta 1 constant, and first one slope coefficient. Okay, regression coefficient, beta 1. So if you have 1,000 samples, or say 10 samples of 1,000 size, you will have 10 different estimates of betas. So if you keep doing that, then you can create a distribution of those estimator themselves of beta 0 and beta 1 and beta 2, whatever betas you have, however many beta you have. You can create an actual sampling distribution of those betas, regression coefficients. If you keep taking out sample of the same size from a given population, large number of times, say 1,000 times, 5,000 times, you do it 10,000 times, you do it 50,000 times, you do it 1 lakh times. If you keep doing that, you will have large number of estimates of betas in your regression analysis. Okay, beta 0, beta 1, beta 2, let's say just beta 1. So you will have 10,000 estimates of beta 1. How each beta 1 came? Each beta 1 came from a sample of 1,000 firms. So if second beta 1 came from a new sample of 1,000 firms, some can repeat, fine. Third beta 1 came from a new sample of 1,000 firms. Previous firms can repeat. Okay, that is why we call it repeated sampling. So you can create a sampling distribution of that. That sampling distribution should follow these 8 properties, or at least the last, the property from fourth to the last one. Okay, if they follow these 8 properties, okay, then we call it to be a good estimator. Okay, its cost should be low. It should be least squares. So the every time you estimate regression, see, you have a sample size of 1,000 firm and you are running it, say 10 times. Every time you run it, you will have a residual. Okay, you will have an error term, a residual estimated error term. Okay, so you want that error to be as low as possible. How do you keep it low? We will see that right now. There is one technique, OLS. Okay, so you want that error to be as low as possible. R square is how well your model explains y variable, how well your x variable explains y variable. You want an estimator which can explain your y variable in the best possible manner amongst all other estimators. Okay, unbiasedness implies as you increase the sample size, not the number of samples. Sample size is 1,000. Now you increase it to 2,000. Now we increase it to 5,000. Now we increase it to 10,000. As you keep increasing the sample size, the estimated betas based on the estimator, that should come as closer and closer to the population parameter. then you have a good estimator. Otherwise, your estimator is not good. So I have a recipe, I start creating bread, but every time I run that recipe, my bread comes out either burnt, or it is not smelling good, or it is too hard. So that means my estimator is not good. What we want is an estimator where if we keep making breads, if I keep making bread, every time I make bread, on an average, that bread quality should be as close as possible to what the market or customers expect. That's the idea behind unbiasedness. Efficiency means the error in this process should be as low as possible. Okay, your error of the estimator. Where does this come from? It comes from the sampling distribution of the estimator. That experiment, repeated sample, keep drawing out sample of 1000 firms from those 1 million firms, keep estimating the beta coefficient, and then see the distribution of beta coefficient. I will show you right now. You know, that beta coefficient, the variance of that distribution should be as low as possible. So it should be as close, you know, in that bell-shaped curve, it should be as close as possible to the mean value. If it is too wide or too spread out, then you know you are making a lot of errors. Your estimator will be very dangerous. Sometimes your recipe will come out to be very good, bread will be great. Sometimes the bread will be very bad. Sometimes it will be the best bread in the world. Sometimes it will be a hell for people to even look at it. You know, you don't want those kind of estimators. So efficient estimator is whose variance is the lowest. Okay, mean square error and the last three you don't need to get into right now. Once you read more, you will be able to get it. But the first five should be fairly understood by you. I will show you in diagrammatically also. Okay, I will show you diagrammatically also. Yeah, I am going to show you. Ritika is asking, if population data is not available, how do we know about beta and compare it with sample beta? It makes an assumption. That is the beauty of OLS. We don't know econometrics. That is the beauty of econometrics. We don't know anything about PRF, yet we can make an estimate about PRF, assume how PRF would be, and compare our sample with it. That is how OLS estimator works. It works on the sampling distribution of the beta. You know, I told you not, take out 1000 size sample multiple times from the population, and you create the distribution, sampling distribution of that beta. You take its distribution, let's say it's a bell-shaped curve, take its expected value, mid value, that's the population value. Okay, so it dummifies population through the sampling distribution of estimators. That's the beauty of econometrics. Okay, even though we don't know anything about population regression function, we can make comment on how close our estimates are to that. Okay, so some quick questions for you. You should be able to answer this slide in your mind. No need to type the answer in chat box. Don't unmute yourself. Just answer in your mind. We need to use SRF so that we can estimate the PRF. Those who understood, correct. Okay. Dash will also contain regression coefficients, but they will be estimators of PRF regression coefficients, matlab parameters. So the answer is SRF. SRF will contain regression coefficients, but they will be estimates of the population regression coefficients, which are our parameters. So which estimator to use? OLS, the emperor of econometrics, or maximum likelihood, or there are a lot of others, two-scale least square estimator, instrumental variable estimator, but those are used when you have very strong reason not to use OLS or MLE. Okay, very important. So OLS is an estimator, it's a formula. And the idea behind OLS is your actual observed Y, that is your sample data. In your sample data, you have Y value, okay, which is what you are interested in. In our example, corporate profit, it's what we are interested in, okay, the effect of corporate tax on corporate profit. So we are interested in corporate profit. So we'll collect data on corporate profit. Then we will run a regression of tax on corporate profit, estimate corporate profit using that equation. The gap between them is your error, okay. What OLS does, firstly, it squares it, sums it up, and then minimizes it. So OLS is an estimator or a formula to estimate those beta coefficients, where after estimating those beta coefficient, whatever error you have, the square of those errors, when you add them, a big number will come. It will be the most minimum one. So you will have different options to run this. You can use maximum likelihood estimator, you can use instrumental variable estimator, or anything else. There are hundreds of menu. It's a big menu, econometric menu. But in econometric menu, OLS will minimize. It's the most efficient one to minimize, the best one to minimize this particular equation. That is the square, sum of the square of residual. So every time I run a regression equation. I will estimate beta coefficients and estimate my y, which is my forecasted y, estimated y. It will never be equal to my actual sample data y. The gap, square it, add it for all y's, and then you will have a number which is this given here, sigma yi minus y cap square. What OLS does, it minimizes this. Why doesn't it do something else? Why don't we? This is required everywhere. You want to minimize this one only, whether it is OLS or MLE or something else, you want to minimize this one. In most of the cases, OLS can minimize this kind of error. In some cases, it cannot. So you use some other method which can minimize, which is better at minimizing this kind of error, like MLE or instrumental variable. Okay. In those situations, OLS is not capable of minimizing this error. So you use some other one, other technique, some different econometric technique. But you should have that strong reason that OLS will not be able to minimize this. Okay. That strong reason has to be there. Fine. This is how, this is what we mean by residuals. You can see the idea of residuals here. All right. The estimated regression line is here. Your forecasted y value, your forecasted y value is given here, that bold line. And then your actual y value will not be exactly. Actual y means the sample data, actual y data that you have, based on which you estimated this equation. There will be gaps. Okay. U cap 1 is the difference between y value of y, actual y at x1 and the estimated y at x1. See, y can only be estimated or observed when there is an x value. So when you have sample data, for each x you will have one y. For second x you will have second y. Similarly, for each x you will have an estimated y also after you have run the regression. So two y's will be there for each x. So for x1 here, you have y which is on this line, which is your estimated y, your regression equation y. And there is on the top, there is one more point, which is the actual sample data y, which you have seen, observed against x. The gap between them is the residual. You square that residual, add all of them. Why you square it? If there are some reasons, you read the reference thing material that I'll give you, read them. Okay. Once you square it, you give more importance to the larger errors, less importance to the smaller errors. Okay. More importance to the larger errors and less importance to the smaller errors. That's the beauty. So you then add them together and you minimize that number. Whichever estimator can minimize it in a given situation will be the best one. In most of the situations, OLS can do that. If OLS is not able to do that, you need to find some other estimator, some other formula, some other recipe to create your bread so that it is as close as possible to what the market or the customers want. So find out some new recipe. Maybe you are putting wrong yeast. The ingredient you are using is maybe wrong. So your estimator needs to be changed. So you have to leave OLS behind. Otherwise, OLS should not be sacrificed. Okay. Otherwise, OLS should not be sacrificed. This is an experiment that I told you. You have sample of y and x. Now don't take out new x and new y. Keep the y and x same. There are two equations shown here at the bottom of the screen. I don't know if you can see. I'll increase the size. Okay, there are two equations shown here. Y cap 1i and y cap 2i. In both the cases, if you see the beta coefficient b0, it is different and b1 is different. Earlier it is 1.572 and 1.357. Then it is 3 and 1. So you keep collecting, keep putting new beta value, different beta values, and every time you do that, okay, every time you do that, you will have a new u square or residual square, u cap square. That sigma y minus y cap square. That this is 12.2 here for the first equation where the beta value are 1.572 and 1.357. The second time it is 14 when it is 3 and 1. So now you asked, so what are these two? Let's say the first equation was estimated y1i, okay, this 1.572, this 1.572 and 1.357 was estimated using OLS. And you decided, no, I don't want to just depend on OLS. I want to use something else also. So you use something else, the maximum likelihood estimator. And there the beta comes out to be 3 and 1. Now you find out the sigma y minus y cap square, residual square. In the first case, it is 12.2. In the second case, it is 14. Now, which one should you select? In this case, which one should you select? Definitely the one that minimizes your error, which is the first one, which is 12.2 wala, the one which is showing the residual square to be 12.2. That is the one you should select. So econometrics is actually a science about which estimator to select in which situation. Okay, which estimator to select in which situation. That is the fundamental idea behind econometrics. This formula I will not talk about. You read about it. It will take too much time. We have very less time. Okay, we are having a 2-hour session. I could extend it, but that depends on Dr. Malik and his team if they form. But yeah, the idea, if you see the numbers, they're X and Y's. Which are X and what X and Y's? The sample data that you have on X and Y. So OLS is quite easy to compute. That is why even Microsoft Excel estimates OLS. Okay, so it uses actual observed sample data, plugs in. This is the recipe, the formula, the recipe of creating the good bread that we were talking about. This is the recipe. OLS is this. What is it? How it is made? Too dense question. Maybe we can discuss later with me, or I'll give you reading material. You can definitely go through it. But what are the features of it? Based on sample data, so easy to estimate. Does not need any new hi-fi, like in Monte Carlo simulation. You need to estimate things and create scenarios. You don't need to all that. Use your actual data. It uses cross correlations and covariances. Very simple statistical concepts you have studied in Dr. Parmeet's lecture. Standard deviation, variance, covariance. Those things are used here. So basic statistics can be used to estimate these, and they are very easy to compute. You can see the formula. You can work this out on calculators also. And in my class, for example, I teach them sometimes in calculator how to calculate these coefficients in regression lectures. So it is very easy to do that, and it is inbuilt in all econometric technologies. So what makes OLS the gold standard in econometrics? 3 major properties. There are the numerical properties. The numerical properties do not require any underlying assumption, the classical linear regression model assumptions. They don't require that. Statistical properties require that. Okay, in statistical properties, you need to understand how your X and your error term are generated. They will affect how the estimator works. If your X and your errors are generated in a very different manner, then OLS may not be the correct estimator at that time. Okay, so numerical properties are very simple properties. They don't need any such assumption. Statistical properties require that assumption. And then there are some epistemological, or what I call philosophical properties of OLS, why they are good. All right. So these are the numerical properties. No need to get into deep. Okay, we will not have enough time then. But they are point estimators. There can be interval estimator also. You can have a range of coefficients. Like if you estimate regression in any technology, you will have confidence interval range, upper and lower range. So you can have a range also interval, that your population value should fall in this range only, with say 95% confidence or 99% confidence or 90% confidence. Okay, so OLS can be point estimators. You can also have what we call interval estimator. It's very easy to estimate in any package. We will see in Eviews also. These are some of the properties of OLS. I will not get into them in detail because of time constraint, but I'll share the PPT. You study and you always contact me and discuss with me what does this 3.1 mean. Okay, the 3.1 says that on an average, the actual Y and estimated Y will converge. So the error will become smaller and smaller. What does it mean? As you keep increasing the sample size, this will keep on happening. So your errors will become smaller and smaller with increasing sample size. The next one is that mean value of your residuals, your actual sample regression equation, which you are actually estimating. Those residuals, that mean value will be 0. So they will cancel out each other. They will here they will cancel out each other in this graph. This U cap 1, U cap 2, all put together. If you add them, don't square them, just add them. The total will be 0. So they don't have any systematic influence on Y. They are there, but they will not have any systematic influence on Y. And lastly, the residuals will not be correlated with Y or X. So homoscedasticity is expected. That is, your residuals, errors, will not have any systematic relationship with either the Y variable, dependent one, or the X variable, that is the independent one. This is very important. Now, our last part of the discussion, the classical linear regression model. What do we mean by classical linear regression model, and why is it so important? I have taken Peter Kennedy's book as a reference. I have put the reference names also. I will share these books also with you. So do read about them. See, what is a good estimator? We saw some criteria. We saw some criteria about good estimators here. Here, we saw some criteria about good estimators. How are they good estimators? These are based on the sampling distribution of those betas. Keep taking out sample of size 1000 from the population and keep estimating the beta coefficient and see sampling distribution, that should follow all these criteria. If you use OLS estimator and it follows these criteria, OLS is the best, thumbs up. If you use OLS and some of these criteria are not applicable or fulfilled in the sampling distribution of the coefficient itself, then you need to go for some other kind of estimator. That's the idea. But under what circumstance? Okay, under what circumstances? Okay, what are those circumstances or situation in which OLS will tend to be the best one? Or what are those circumstances in which a good regression equation can be estimated? Okay, you need some criteria, some set of standard. Okay, in this situation, my analysis will be the best one. In econometrics, what are those? What is the situation? It is known as the classical linear regression model. Okay, to take or hypothesize repeated samples, knowledge of the way in which observations are generated is necessary. So if you are taking out samples every time from a population, you should know the process through which the sample is to be generated, because you don't know the population. So you will have to extract sample from that population. So you need to create an equation also for that extraction. Now, unfortunately, an estimator does not have the same characteristics for all the ways in which observations are generated. Okay, let me have water. Unfortunately, an estimator will not have the same characteristics in all the way in which observations are generated. Very important to appreciate this part. If observations are generated, so what we mean by this? If X is and residuals are being generated in some other manner, then OLS estimator may not be the best one. Okay, then OLS estimator may not be the best one. There is no super estimator. Okay, an estimator that is the best in all situations. Okay, whatever you bring, whatever kind of data you have, whatever errors you have done, whatever problems are there, there is no single estimator which will be the best one. There will always be estimators which are good in certain situations and which are not good in certain situations. So the researcher facing a particular estimating problem will turn to the menu catalog of econometrics, will find what kind of situation am I facing, what kind of data I have, what kind of X variables I have, what kind of process may be going on. And based on that, a good econometrician, good empirical analyst in social sciences will decide which estimator to use. By estimator, we mean the which econometric technique to use. Okay. So what are those situations? Those are this classical linear regression model situation. Okay. This situation, how to choose a good estimator. Okay. How should a good estimator behave? What are those criteria? Okay. What is the situation, that environment in which every estimator should, whatever estimator you select should behave well. Okay, that is should fulfill those 8 criteria we saw. What is the situation? Those situations are known as CLR, classical linear regression model assumptions, or classical linear regression model. OLS is the best in all form. It is the blue, best linear unbiased estimator. One more assumption is required, but we'll get that. OLS is the best if that CLR assumptions are followed. So your question comes, what are this? What is the CLR? Okay. Ajay Gidwani, wait a little bit for hands-on. Don't be so concerned about softwares. Software is nothing big. It's a matter of 10 minutes. You should learn about the fundamental foundations and the theory. Unless you know theory, just simply running softwares day and night, it will make you feel very great that you have run something, but it will not make any sense and you won't be able to publish in good journals. So try to understand the fundamentals. We will definitely cover hands-on. We can always put hands-on on some other day here and there also. It's not a big issue, okay? But try to understand the fundamentals. Hands-on is my responsibility. We will definitely do it. If we are not able to cover today, I will definitely conduct it during the workshop somewhere for say 30 minutes or 40 minutes. Okay, don't worry about hands-on. I will teach you, but try to understand the foundations. Otherwise, you know, in India, we have, not in India, across the world, we are having large amount of research work going on, but there is no sense or foundation or logic behind it. Quality is not there. So you need to bring that quality, you need to understand these foundations. Otherwise, you will just go with sample data, put it there, press button, option 1, option 2, option 3, something will come, put that in paper and publish it here and there. And then you will see that you are not getting any success out of it. Okay. So econometricians are often not certain, okay, whether the estimating situation they are facing is the CLR situation or it is different than the CLR situation. So there are various tests available. We don't need to get into those tests. So what are those finally, almost the end of the session, the presentation, what are those assumptions? The first assumption that we have, okay, is that it should be a linear regression model. What do we mean by linear? Linear in parameters. So here you have an equation. Y is a function of b1, beta1, beta2, x and ui. X is linear. It is only x. Betas are also linear. But you can also have x square here. You could have x square here. Okay, still it will be linear regression model in econometrics. Why? Because the betas are still linear. But if you have y is equal to beta1 plus beta2 square x, x is still linear, but beta 2 is squared. So now it is non-linear regression or non-linear model. All right, getting it? Very important, this assumption. The second one is x should be independent of the error term. So we don't want x to be dependent on the error term. Why? Because we want to treat effect of x on y separately than the effect of error on y. That is why we say y is a function of x and error. So we want error to have a separate impact on y, and we want x to have a separate impact on y. If both are related, then we cannot take out that separate impact of x on y. So corporate tax and is having effect on corporate profit. But if corporate tax is related to the residual also, the error, then we don't know the true, proper, pure effect of corporate tax on corporate profit. That is the reason we have this second assumption. Don't worry, I'll be teaching, giving you a lot of reading material. You'll be able to understand. The mean value of disturbance in the population or the residual in the sample, it should be 0. That is the error around, see, for every value of x, x1, x2, let's say corporate tax of 10%, corporate tax of 20%, corporate tax of 30%, different firms will have different profit. But on an average, they will be at the mean value of their distribution. So at x1, there will be 1,000 firms having different profits. The actual value, the error, that is, you see the points which are above this line, and you can see the points below this line, they will cancel out each other. So it will be there, but the overall distribution will show that it is hitting the midpoint, the central point. Yeah, I'll be sharing the lot of reading material, and that too I prepared it chapter by chapter. I'm not simply sending books. I prepared chapter topic wise. It's a very good material. You'll definitely enjoy it. So I'll share that with you. Okay. So getting the idea. So at each x, there will be different y values. So the difference between the estimated y and the actual population y is your error, written here as u cap plus u and minus u. On an average, it should cancel out each other. Okay, so the regression line should pass from the middle of this. That's the idea. So there is no systematic error. Suppose if this error is expanding with time, okay, like this. Suppose if the error is changing with time. In the first example, in the first graph, the distribution of error is constant. It is not changing with x. As you move from x1, x2, xi, it is not changing. However, in this case, in the second case, it is changing. Sometimes it is decreasing actually. It is decreasing the variance, the spread of the error around its mean value, this straight line for each x. As you move from x1 to x2 to x3, it is flattening. So it is increasing. The error is increasing. The nearer it is to that straight middle line, the less the variance of the error is. So in the case of x1, say corporate tax of 10%, there are firms with very less variation. They are largely near their average value. Say average profit at that level is say $500 million. So most of the firms are not at $500 million, but they're very near it. But as you increase the corporate tax rate, you see a wide diversity in the firm profit. Firm profit becomes more and more dispersed. At 20% x2, there are firms which are having very low profit, very high profit. At x3, 30%, there are firms with very, very large profits or very, very low profit. That is changing systematically with time. Your distribution of error, or in other words, distribution of y is changing drastically at that point, across the x values. That should not happen. If that happens, then your error is having some systematic component. There are some variables missing. You should have included those variables in your study. So it is known as homoscedasticity. If it is violated, it is known as heteroscedasticity, and you will be happy to know we have a separate session on it. So if this happens, what to do? Can you use OLS? Yes, you need to test for heteroscedasticity, correct it. If you can't correct it, there is no possibility, then you go for some other estimator. Okay. Similarly, autocorrelation, this is useful for time series data, generally not much for cross-sectional data. If error terms are related with each other, you can see here, if past error is immediately related to the next error, okay, at different values of x, then errors will show a systematic pattern. The first two ones, A and B, we don't want this kind of pattern in error. We want this third one. So errors are not systematic in nature. That is known as not autocorrelation. When high variance data is presented, then how is it possible to fit? You need to do variance decomposition, variance correction. Do get back to me, Dr. Raja. I will explain you various ways of handling it. There are a lot of ways to handle it. Then if you're using time series data and there is a lot of variance, you can go for conditional this Garch and Arch modeling methods, where you take into account heteroscedastic variances and you model those heteroscedasticity. So heteroscedasticity, suppose if errors are like this A and B, it's not bad. If you want to work under CLR assumptions and use OLS, you need to correct for heteroscedasticity. Otherwise, you can use alternative estimators, Arch or Garch estimators, and then you can actually use that heteroscedasticity and take advantage of it, in your data. Fine. Last few assumptions, then we'll go quickly on hands-on. The number of observations should be greater than the number of parameters. If you are having only one y and one x, and you want to estimate 5 regression coefficients, it's not possible. You don't have enough data. You don't have enough data. Arshiyaji, the Durbin-Watson test is for autocorrelation, but it's not completely reliable. For example, if you are doing dynamic modeling where you have lagged value of the dependent variable, y lagged value as a regressor, then you can't use Durbin-Watson. And there are a lot of other Broich-Gottfried tests, other tests which are superior to Durbin-Watson in terms of their asymptotic properties and other things. So yeah, it is correct. When you discuss about autocorrelation, Durbin-Watson will be a very important topic to discuss at that time. Finally, the x variable nature. X variable should not have, your regressors, independent variables should not have very extreme values. Otherwise, they will end up creating heteroscedasticity or some other kind of problems. For example, if your or most of your or 99% of your x are within a range of 5 to 10, and there is one x which is 50,000. So you can understand it will completely change the regression coefficient of x on y. And if you remove that big number, then you will see the picture is completely different. Earlier it was not significant, now it is showing significant. So check for outliers. We don't want very extreme outliers. So these are the assumptions put in a very nice, compact, tabulated form. You will get this PPT and reading material. You can sit down slowly, gradually. That is why I told you today, have coffee and tea. Okay, you will be able to understand. See, it is also written, if it violates, what kind of condition occurs. So in these cases, there are two options. Either you correct for these violations, correct them and continue with OLS, or if that cannot be corrected, then drop OLS, find the better alternative like maximum likelihood estimator or heteroscedasticity and autocorrelation adjusted standard error method. A lot of other stuff is there in econometrics. So again, the same thing, no need to repeat this. You read this in the PPT, same assumptions written in a more compact form from a different reference book. Very important before I end this discussion, a variant of OLS is known as stepwise regression. You should be very careful with this. You take one x and run it on y and see whether it is significant, r square is high. Then you run y on x, then you see where r square is high. Wherever r square is high, you choose that one. So causality is thrown into dustbin. You decide causality based on data mining. So econometricians hate that, and they claim that statisticians generally get into all this data mining techniques, but econometricians don't like it. Okay, so you should avoid that. So finally, what is the CLRM statement? It's known as the Gauss-Markov theorem. Okay, in Gauss-Markov theorem, the least square estimator are the best linear. They are the unbiased. In all the unbiased linear estimator, they have the minimum variance. So in other words, they are blue. So if those conditions, which conditions? So 7 assumptions that we have seen here, this one, if they are fulfilled in whatever data set you are examining, if you can think about them and if you have theoretical reasons, yeah, these problems will not be there, then OLS has the property known as blue based on the, and this theorem or this principle is known as the Gauss-Markov theorem. So OLS has the best property. Okay, here is the idea of being unbiased. The distribution of beta, which is the estimator, OLS estimator of regression coefficient beta 2. Okay, it is having unbiased estimator because its central value, its average value falls on this dot, which is equal to the population value. Okay, and let's say you have two different estimators, OLS and let's say some other estimator, call it Bhagirath estimator. In graph C, you can see OLS estimator and Bhagirath estimator. The beta 2 is the population parameter, population value, what you are interested to find. So both are unbiased. Why? Because both have their middle value as the population value. But which one is better? The one which has lower variance. So the one with the clear, clean black line is the one which has the lower variance, which is generally the OLS estimator. If the CLR conditions, CLRM conditions are fulfilled, that is the Gauss-Markov theorem is applicable in this cases. So OLS will be the best one. Always go for OLS. One problem is with this, you can't do hypothesis testing. So in order to do hypothesis testing, you need to go for one more assumption, that your residuals are normally distributed. Then it becomes classical normal linear regression model. And in this case, though, OLS is absolutely superb. Until you can maintain normality of residuals, if some other things are not followed, still you can manage and continue with OLS. See, even if you use OLS in these situations, your results are not going to be bad per se. You are losing efficiency or unbiasedness. It's a trade-off. If as an analyst you are fine with efficiency, you want it to be unbiased, you can continue using OLS even if there are some violations. Okay, so if you understand all these things, you read and you will understand. What are the philosophical properties of OLS? Why I find it to be really fascinating. It's the most innovative method or discovery in quantitative science. It avoids any subjective choices of econometricians. Other estimators require it to choose various parameters in advance, like Bayesian techniques and other things. You need to choose certain things in advance or priorities. Those kind of subjectivity are avoided. Actual sample data will decide. Actual observed data will decide the truth. Okay. So you do read about this. What is the road ahead? Read the books that I will share you, the reference material I will share you, my PPT that I will share you. And remember, last statement, whenever there is a violation of the CLRM or CNLRM assumptions, those 7 assumptions plus that residual should be normal assumption, 8 assumptions, don't immediately jump to some other estimator. Try to understand what will happen if you continue using OLS. How can you correct these violations? And as far as possible, try to bring in OLS. Once you are sure it cannot be done, then only go for two-stage least square, partial least square, or instrumental variable estimators, something else. Okay, only then you do it. Finally, what you all were waiting for. Okay, for God's sake, let's start it now. And I have installed the Eviews. I will not be able to show the installation again. Some people are asking that. I already showed it. I started 15 minutes in advance. Showed it. Some people are facing problem. You contact me personally. I will guide you how to install it. Okay, tomorrow I will guide you. Personally, you contact me. So let's go on to Eviews. Those who have installed can take advantage of this. Those who have not, just have a look at it. You will definitely be able to understand it. Dr. Malik, 10 minutes more. And Mr. Owais, 10 minutes more. Okay, then we will end.
Sure, sir.
Yeah, 10-15 minutes more. So today you give me a little bit of leniency because we have discussed too much of dense topics, and this is important to discuss also. So let me share a screen with all of you. Where is it? Yep. Let me share the eView screen with all of you. All right, the final thing that you all were really waiting for. This is your simple old eView screen. A very wonderful econometric technology, very sophisticated, can handle large data sets also, but not as good as Stata or R, but can definitely handle large data sets. This one is quite good for time series modeling. That is what I feel. My personal view. Many others might say it is good for panel also. For panel, I feel Gretel is good. Stata is also very good. For more advanced time series modeling, you can go for JMulti or Jamovi is there. Those things are there. But if you know Gretel well, it is enough. Don't learn too many softwares. Okay, learn 1 or 2. That is more than enough. Excel is compulsory. You should know Excel very well, and 1 or 2 more advanced technologies. fine. Otherwise, you focus on the foundations, the theory, the understanding. Believe me, if you develop that, you will be able to create very good research, which has good impact. And it takes time. Good quality research will take time. So let us look at the Eviews screen, which is visible in front of you. The same data set we used yesterday, I will use the same data set. Now it was in Excel, not in Eviews file. So we will have to import it. So we will go to the option file in Eviews, go to the option file, go to the option import. All right. Let me remove all the screens in front of me, the Zoom screens. Then in this, again, file, import, then we take the option import from file. I click on that. Once I click on that, menu is opened. Okay, a menu is opened. I will select my file wherever it is. I will go to that particular folder directly and I will select that file. This is the file 1510-2024 dataset Dr. Bhagirath. This is the file you also must be having, yesterday's file. It is in Excel. I will press open. Once I press open, it will again ask me, like Gretel, which sheet you want to bring in. We want the first sheet, the sheet having the word quant. So we want that sheet to come. Now it will show the data set in front of you. How is it looking? You can have a quick view at it. Very important that numbers are visible here. If numbers are not visible, go back to your Excel file and make the corrections or adjustments. All right, numbers are fine, visible. You go on the next one. Now on the next one, it will show you each variable and what is its nature. How is it defining or identifying the variable? How is Eviews identifying the variables, the numbers that you have put from that Excel file? So you can see it is identifying it as a number. Okay, it is identifying it as a number. You can also identify it as a date or character, but in most of the applications that is not the case. Yeah, in management side where they have sales data, product sale, marketing campaign data, they can have data on dates, they can have data on other things. There they might require it. But in most of the social sciences, numerical data will be expected. What if you have text data? What if you have video data, audio bit data? Then you need to go for big data modeling, okay, which Mr. Lucky and Mr. Dwarkesh will explain you later on. So this is also visible. Great. So we go ahead. Now, see, now this problem is occurring. You know, this problem did not occur yesterday, it is occurring. This can occur with you many times. This problem occurs many times with you. You are not able to see your data. It shows NA. Somehow it is unable to read it. One of the limitations of cracked Eviews is this. Okay, so whenever this happens, don't worry. You check the variables, whether they are specified correctly. Okay, whether it is identifying it correctly as numbers. If not, and it is still showing NA, you need to close it and restart it. Just a moment. I am again sharing the screen with you. My Eviews is loading. Just a moment. Yeah. So my Eviews is on. I will again reshare the Eviews screen. No, 16. I have another data set already ready. So the same file, import from file, and I have already kept that data, but I have numbered it separately. I think it was 16. I don't know where is it lost. No problem. Fine. So it is 15. You press open. Let's see if it is reading now. Yeah, it is reading now. Okay, so data is readable. Sometimes this may happen. So close down your Eviews and restart it if NA values are shown and press finish. Press finish, maximize the screen. Now you have this Eviews environment in front of you. What it shows, it firstly shows all your variables. But in Eviews, it's not like Gretel. In Gretel, whatever the order you have of columns in your Excel sheet, Gretel will follow that. That's not the case in Eviews. Eviews says, I don't care. I'm a premium software, I'm a premium tool, so I will go according to my wish. So what it does, it arranges it alphabetically. Okay. And the C term is the constant term, no need to touch it. Resid is the residual. It will be estimated every time after you run a regression. Eviews will keep automatically updating the residual and the C component every time you run a regression. Other things are your main variables of interest. And here above that, you can see the range of the data that is, there are 6,607 observations, and the sample that you are using. Like in Greater, you could change the sample size, you could reduce the sample size, truncate it, take certain portion. You can do that in Eviews also. Those options are available. But generally, we don't do that. We already have data on about the sample with which we are actually interested. Okay, but sometimes you want to run t-test or a chi-square test or f-test between two samples, or run regressions for two samples within two subsamples and then compare them. Those cases, this kind of options are very useful. I still prefer Greater at any point in time, if you ask me. So then you have other options, what all operations you can do: view, process, proc is process, object, save, freeze. That object, if you click, you can generate a new object. Eviews has large capability. You can generate many different kinds of objects, text, table, lot of things are there in Eviews. I mean, it's a very massive software, and that is why it is so popular also. Achha, how do you, achha, there are options of file. In file, you will see all typical options of a typical program: open file, or save this, or save as the file as an Eviews data file. Edit option is there, very simple. Object option, again the same. You can create objects, new series or new text, something like that. Generally, you will use it to create new variables, standardize a variable, or create interaction terms of two variables, something like ratio of two variables, like GDP per capita. You have data on GDP and population. You can divide them through this formula. You can use it, but still it is very easy in Greater to do it. Sorry for my Greater bias. Then you have view option. Fine, very basic. Statistics shows you how much data you have, what are the data points, etc. No need to really be bothered about it. Once you do something and you want to go back to the original data, go to the option view and click the option work file directory. Okay, so if you do some operation, new screen comes, always go to the option view and go to the option work file directory. It will bring you to the main work file workstation where you are handling everything. Now, what I want to do is, I want to again estimate that regression that we have done yesterday in Greater. Fine. So what I'll do here, you need to be careful. The way you click one by one each variable, that is how Eviews will recognize it and load it in its system. Whichever you click first, it will recognize it as the dependent variable. So you have to be very careful which variable you click first. So I'll click exam score first, our yesterday's example about student performance. Then others are fine. You can go on in any direction you want, but exam score should be first. Then on any one of the selected variable, you can press right click. Okay, not left, right click. You see the option of open. Now in open, you have several options. You can open it as a group. You can directly estimate an equation out of it. You can create a factor analysis. You can go for vector autoregressions in time series data. You create system equations, VAR systems, or you can even create simultaneous equation systems. You can open them as multiple series separately, whatever you want. We generally go for open as a group. So why we do that? This helps you to visualize, see your data in front of you. You get to see your data in front of you, how it looks, what it is. Are there any abnormal numbers here? You know, you can, of course, there are a lot of other things available in Eviews to catch those things. But yeah, you can see all those things here. So the first thing comes is, whenever you have data, you want to, and assuming that it is in the form that you want it finally in your analysis, you want to see its descriptive statistics that Dr. Parmit must have talked about. Your mean, the average value, the minimum, the maximum, the standard deviation, the kurtosis, skewness. Each variable will have a distribution. You want to get a feel of that. You want to see if there are some extreme numbers, too much of variability in data. There should be variability in data. It should not be too much. That's all we are talking about. So you can go to the option view after opening the, again, I'll show you the steps. Okay, I'll close this. We have data in front of us, workstation. You select the first variable, which is your dependent variable. Eviews will recognize the first click as the Y variable. Then click other variables in the order you want or directly. Don't select residual or constant. Then right click, open as a group. You have your data in front of you. Now we want to see the descriptive statistics. So go for the option view. Okay, go for the option view, showing you here. Then go to the option descriptive statistics. It asks you a question whether you want to take common sample for all, or so uniform sample, or you want to take sample size equal to the number of data points available for each variable. What I feel in my research, I tend to, for descriptive statistical analysis, I tend to take individual samples, not common samples. Okay, why I do that? Because I don't want to suppress information. If there is less information on something, let it be. But if there is more information, I don't want to trunk twist information, cut away that information. Okay, that is my idea behind it. So you can go for individual samples or common.
Sir, it
I'll
is
go
not selecting all variables as you did.
Pardon, what is happening?
Sir, when we selected another variable,
Yeah.
so our first one was unselected.
No, you keep the control button pressed. Keep the control button pressed, and then you click on variables one by one. Then it will get, it will select. Yeah. So again, I'll repeat the step. You have selected first. The first click is your y variable. Others are your x variable. How you selected? Select the first one, your y variable. Then keep your control button pressed in your keyboard. Then you select other ones. Okay. Keep the control button pressed. Select other ones. Right click. Open as group. You see the data in front of you. Go to view option. Okay. Go to view option. Descriptive. Go for common sample. Okay, if you want to keep consistency, or I'll prefer individual sample, I'll go for individual sample. Now you have the descriptive statistics in front of you. Okay, how to interpret descriptive statistics is what Dr. Parmit had talked about in the session. I will share some good reading material, but the fundamental idea, Rupanshi, behind descriptive statistics is to know first, is your variable well behaved? That is there too much of variability? It's a variable, so it should vary. If there too much of variability, you want to see that. Are the variables showing non-normality? Are each of the variables normal or not? That is
So
something.
sorry, sir. Sorry to
Yeah.
interrupt you, sir.
Yeah.
Actually, we are running out of time, so
Okay.
we have just last couple of minutes. So please,
Yeah,
if you
sure,
can
sure.
wrap up.
We won't go for any question answer round. I have already taken many questions, so we can after the end.
Thank you.
Yeah.
Thank you.
Yeah, and participants can send the questions to me personally. I'll answer you in this week, by this weekend, for sure. I will definitely answer you. Already I am handling a lot of questions during the session. We have less time. So you send me questions personally, I will definitely answer your questions. Don't worry. Rupanshi, do get back to me. So fine, this is how you have descriptive statistics, and it directly shows you the normality test, Jacobi-Baria test. Okay, very important to read about it. It shows you the mean value, the median also. Cross-sectional data, median is also important at many times. Mean, max, standard deviation, skewness. It shows you how many observations are there on each. We have complete data set, so great. Now, what we want to do, the last thing, we want to make an equation, estimate an OLS equation for this. So we go to the option proc here, or you can go on this side also, anywhere you like. I'll go on this side, proc. Okay, make equation. As soon as you click the option make equation, it will automatically tell you which variables are there, and the first variable will be the one that you had clicked for the first time in the initial selection. And in this window, it will ask you what kind of method you want to use. There are so many methods in Eviews. Just look at it. Now again, remember, all these are not methods, they are different estimators. Equation is the same, they are different estimators. If that CLRM condition is not being fulfilled, you go for say TSLS estimator or GMM estimator or ILIML estimator or co-integrating estimator or arch or binary or ordered. Those assumptions you have to see, are they being followed? If they are being followed, keep quiet and go for least square. If not, then start looking for other ones. All right, so we go for least square, assuming that those things are followed. You select least square and just press OK. Once you press OK, you have this data in front of you, the final regression estimate, and it shows you just like Gretel. It shows you the dependent variable, which method you have used, least square or TSLS or something else, the date on which you have done it, the time at which you have estimated it, the sample range, number of observations, your coefficients. It shows you the R square, which is 0.59, quite good for this kind of data set, cross-sectional data set. It shows you the F statistic, highly significant. The larger the F statistic, the more significant it would be. The overall model is quite good. The overall model is capable of explaining exam score. So if you want to improve exam score of students, you can use these variables. One variable is not significant, sleep hours. Don't remove it from your data. There is a habit, people insignificant, drop it. No, report it. Also estimated without the insignificant variable, but also show the result with insignificant variables also. Okay, that is also a finding. So not try to hide it as a good researcher. Okay. Recid you should not use. Recid you should not use only. Recid you should not click. Recid is not a variable to be click. I told you, Aarti, in the very beginning. Okay, redo everything. Don't select recid. Recid and C constant are not to be selected from the main workshop screen, work file screen. Yeah. So this is the output. Durbin Watson 2.00. Of course, in cross section we don't really expect much worry about autocorrelation. Generally, it's not a problem, so it's not there. T stats are given. R square is important. Adjusted R square is also important because degrees of freedom are so large. Adjusted R square and R square are quite near to each other. The standard error of regression, the standard error of the whole regression model is shown here. All right, very important to see. Log likelihood will be used when you have multiple models with the same dependent variable, but say different independent variables. You want to see which one is the best one. At that time, you can take advantage of log likelihood. It would be negative. The larger it is, the better that model would be. To get back to me, Arshia. All right, Mr. Owais and Dr. Malik, I'm done. I think we can end. Others who are having queries, please get back to me, and I will definitely help you. Don't worry, I'm there for you. All right.
Thank you so much, sir. Participants, please feel free to type your questions directly to speaker as we are running out of the time. I'm sorry for the inconvenience caused with this. Again, thank you so much, Dr. Baria. We are immensely grateful for the enlightening contribution to our understanding of complex concepts in the econometrics, including the causation, regression, and correlation. And your ability to present these intricate topics in a clear and accessible manner has greatly enhanced our comprehension. Thank you for your invaluable guidance and support, sir. We are again heartfelt gratitude to President JK Economic Association, Dr. Malik, for unwavering enthusiasm and support for the budding researchers. Your willingness to deliver lectures across the various platforms and conducting workshops like this are truly commendable. Your contributions are greatly enrich our academic community. Thank you once again for your dedication and your inspiration. We are also sincerely thankful to all the participants for your attentive listening and discipline throughout the session. Your engagement and commitment significantly contribute to the success of today's session. We appreciate your participation and support. Once again, thank you all.
Thank you. Thank you.
I'm now requesting the IT team to please stop the recording of this session.